Welcome to lecture number 20 in our course on Introduction to Transport Processes, where we were in the midst of our discussion of the technologically important problem of the flow in a pipe. And what I had promised you was to get a relationship between the friction factor and the Reynolds number for this flow in a pipe. If you recall, we had discussed this when we did dimensional analysis. Friction factor is a scaled momentum, scaled by the inertial scales. Okay. And for a pipe at low Reynolds number, we have the relationship F is equal to 16 by Re, and at high Reynolds numbers, there is of course a transition to a turbulent flow. So, we were considering this problem of the flow in a pipe. We took a cylindrical differential volume. Momentum balance, rate of change of momentum is equal to the sum of the applied forces. Okay. And as I said, there is a pressure gradient down the length of this pipe. Okay. So, in addition to the shear stress acting on the surface of the pipe, one also has the pressure forces. As you go downstream, the pressure progressively decreases. That is what causes the flow. And this decrease in pressure basically results in the fluid flow. Therefore, in addition to shear stresses due to the velocity gradients acting on the cylindrical surfaces, both the outer cylindrical surface as well as the inner cylindrical surface, you also have a difference in pressure between the two axial locations. Okay. And that difference in pressure results in a net pressure force acting on this differential volume. Okay. So, this also has to be included into the momentum balance equation. Okay. So, we had written the momentum balance equation and then got the differential form of this momentum balance equation. Okay. Various different ways of writing it, one in terms of the shear stress, okay. And then if you use Newton's law for viscosity for the shear stress, you get it in terms of the velocity itself. Okay. Rho times du z by dt is equal to mu times 1 over r d by dr of r du z by dr minus the pressure gradient. So, if the pressure gradient is negative, that means the flow will be along the plus z direction. So, for a flow to take place in the plus z direction, you require the pressure to decrease as z increases, or dp by dz has to be negative. And then we had used this to solve for the steady problem of the flow in a pipe. In that case, the temperature, the time dependence of the velocity is equal to 0, and I have this equation which basically relates the rate of change of velocity with r to the pressure gradient. Note, this is a fully developed flow. Therefore, there is no dependence of uz on z itself. At a given radial location, if we change z, the velocity does not change. Okay. So, at every z location, the velocity is identically the same. In other words, the velocity profile is parabolic with the same velocity at each location. Okay. That is required because I have to have equal amount, the fluid that is coming in is incompressible. So, volume has to be conserved. Okay. So, uz is only a function of r, it is not a function of z for a fully developed flow. Okay. Similar to the cylinder case, I had a cylinder heat transfer in a cylinder of infinite extent. In that case, temperature was only a function of r. In this case, uz is only a function of r. So, I had solved this equation subject to boundary conditions to get a parabolic velocity profile. uz is equal to minus 1 over 4 mu dp by dz into r square minus r square. Okay. Now, we had calculated the total volumetric flow rate of fluid. Okay. The volumetric flow rate is equal to the velocity times the cross sectional area. Okay. The volumetric flow rate is equal to the velocity uz times the cross sectional area along the cross section of the cylinder. Of course, the velocity depends upon r. So, the velocity is not a constant across the entire cross section. So, as I said, we get a parabolic velocity profile. U z is equal to minus 1 over 4 mu dp by dz times r square minus r square. Okay. It is called a Hagen-Poiseuille flow for the flow in a profile in a pipe. Okay. This flow profile in a pipe is parabolic. Okay. It depends, it goes as 1 minus r by r the whole square. Okay. The net volumetric flow rate is equal to the velocity times the cross sectional area, the volume coming per unit area, per volume transported per unit time, okay, the flow rate, the volumetric flow rate. So, I have to, this is equal to the velocity times the cross sectional area. Okay. But of course, the velocity is a function of r, it is varying as the radius changes. Okay. So, therefore, I have to do an integral over each strip of the area of the velocity within that strip times the area of that strip integrated from 0 to the wall of the pipe. Okay. Each strip of the area in this case is a strip between r and r plus dr. Okay. The velocity within that strip is u z of r, okay, which is basically given here. Okay, u z of r is the velocity within that strip. Cross sectional area is 2 pi r times dr. Okay. So, I have to integrate 2 pi r dr times u z, okay, from the center of the pipe to the wall, r is equal to capital R. Okay. So, you put in this expression for the velocity field into this integral and then actually calculate it. Okay. So, I will leave that as an exercise for you. The final result that you get is minus pi r power 4 by 8 mu times dp by dx. Okay. You can calculate that quite easily. Okay. So, that is the volumetric flow rate, the volume coming out per unit time. Okay. The average velocity is the volumetric flow rate divided by the cross sectional area. Okay. So, the average velocity is the volumetric flow rate divided by the cross sectional area, which is pi r square by 8 mu times dp by dx. Okay. Go back to our expression for the velocity itself. Okay. Go back to our expression for the velocity itself. Okay. This velocity is a maximum when r is equal to 0. It is a maximum right at the center of the pipe. Okay. So, at the center of the pipe, the velocity is equal to minus r square by 4 mu times dp by dx. Okay, let me write dp by dx here. Oh, this is great. Okay. So, right at the center of the pipe is equal to 1 r square by 4 mu dp by dz. The average velocity is r square by 8 mu. That means that u z bar is equal to u z max by 2. Okay. And I can also write this function u z of r as equal to u z max into 1 minus r by r the whole square. Okay. So, the maximum velocity times 1 minus r by r the whole square is the velocity profile. It is a parabolic velocity profile. Okay. Next, let us calculate the shear stress at the wall of the pipe. Okay. The shear stress at the wall, okay, tau z r at the wall is equal to mu times du z by dr. Okay. This is equal to minus 2 u z max r by r square. Okay. This is the wall, this is the shear stress at any location. Okay. Wall shear stress tau z r at r is equal to capital R, okay, at the wall of the pipe is equal to minus 2 u z max by r. Okay. And as we had discussed in the beginning when we did dimensionless numbers, the friction factor F is defined as the wall shear stress by half rho u bar square. Okay. So, this is equal to minus 2 u z max by r into half rho u bar square. Okay. Note that the friction factor is defined with respect to the average velocity, not the maximum velocity. Okay. So, I have to represent the maximum velocity here in terms of the average velocity. Okay. So, if I represent the maximum velocity in terms of the average velocity, I get 4 u bar. I am sorry, there is a mu here. Yeah. By r into half rho u bar square. Okay. So, this I can write it as 8 mu by rho u bar r. Okay. Rho u bar r by mu is a Reynolds number. Okay. However, the Reynolds number as traditionally defined is defined in terms of the pipe diameter and not the radius. Okay. So, if I define it in terms of the pipe diameter d, d is equal to 2 times r. So, r is equal to d by 2. Okay. So, I finally get 16 mu by rho u bar times d, where d is the pipe diameter. Okay. This is 16 by Re, where Re is the Reynolds number rho u bar d by mu based upon the average velocity and the diameter of the pipe. Okay. This also is equivalent to rho times u z max r by mu, okay, because r is equal to d by 2 and u z max is equal to 2 times u bar. Okay. So, the Reynolds number based upon the diameter and the average velocity is the same as the Reynolds number based upon the maximum velocity and the radius. Okay. So, this is the Reynolds number versus friction factor correlation for the flow in a pipe. Okay. When you plot it on a log scale, log Re versus log f, okay, you get a straight line, okay, whose slope is equal to -1, okay, because log f is equal to log of 16 minus log Re. Okay, so, you get a slope of -1. Okay. However, this parabolic velocity profile that we calculated is valid only up to a Reynolds number of about 2100. Okay. Only for low Reynolds numbers, with the Reynolds number Re less than 2100, okay, is this flow through a pipe, is this friction factor valid. Okay. At a Reynolds number of 2100, there is a transition from a laminar flow to a more complicated flow profile called a turbulent flow. Okay. So, in a laminar flow, you have a smooth velocity profile you have straight streamlines, okay. The fluid paths are all straight and you have a smooth parabolic velocity profile. Okay. This profile is of course a solution of the equations. For Reynolds number less than 2100, it is a solution of the equations. For Reynolds numbers higher than 2100, it is still a solution of the equations. Okay. However, approximately at a Reynolds number around 2100, this solution becomes unstable and the system spontaneously goes to another solution. And this solution is called, this is a laminar, and this other solution is called a turbulent solution. Okay. In a laminar profile, the transmission of stress is due to molecular diffusion, okay, due to the kinematic viscosity of the fluid. Therefore, the shear stress is given by the viscosity times the velocity gradient. Okay. So, the transport of momentum across streamlines is by the molecular diffusion mechanism that we had discussed extensively. Okay. In a turbulent flow, actually the velocity profile is no longer parabolic, it is very flat, almost plug like at the center. Okay. In a turbulent profile, the transport of momentum actually occurs due to the formation of a highly chaotic eddies, which are highly fluctuating, highly dissipative. They are basically parcels of fluid undergoing correlated motion within the flow, and these eddies transport momentum in a far more efficient manner than the molecular diffusion, because you actually have diffusion due to the actual transport of fluid across fluid velocity fluctuations themselves. In the case of laminar flow, it is due to molecular fluctuations. In the case of turbulent flow, it is due to macroscopic fluid velocity fluctuations in these eddies which develop spontaneously. Because the efficiency of this transport process is far higher, the stress transmitted is also much larger than in a laminar flow. And due to that, the friction factor is also much higher than what you would expect for a laminar flow. So, it follows the 16 by Re law up to the point at which the laminar flow becomes unstable. Beyond that point, you have a turbulent flow which is highly mixing, highly chaotic, with large fluctuations in the fluid velocity, not just the molecular velocity, but also the fluid velocity. And these large fluctuations transport momentum far more efficiently across the flow, and this results in a much higher friction factor. So, up to about 2100, you can use the friction factor 16 by Re. For Reynolds numbers higher than that, the friction factor depends on other things also, such as the roughness of the walls of the pipe and so on. Velocity profile is no longer parabolic. Near the walls, there is actually a logarithmic law, and towards the center it is plug like, and this results in a highly dissipative system where the friction factor is much higher than what you would expect. So, I have derived for you the friction factor for the laminar flow in the pipe, the 16 by Re law. Turbulent flow is more complicated, and there is no simple form of the friction factor. So, this is a summary of the steady flow in a pipe. Let us take a slightly more complicated situation, and that is oscillatory flow. Oscillatory flow in a pipe due to an oscillation in the pressure gradient. So, the configuration is as follows. I am applying a pressure difference across the pipe, delta P by L. So, if I look at this pressure gradient, so delta P by L as a function of time, this has an oscillatory behavior with a frequency omega. So, the pressure gradient is of the form k cos omega t. So, the pressure gradient has the form k cos omega t. So, that means that the pressure is from left to right for half the cycle and from right to left for the other half of the cycle. Average pressure difference across is equal to 0. The flow is still fully developed in the sense that if I have a coordinate system z and r, the velocity u z does not depend upon z. So, in that sense the flow is still a fully developed flow, but it is not steady, it is varying with time. Because the pressure difference is a function of time, the flow is also a function of time. This is of course encountered in biological systems. In the human body, you know that the heart pumps in an oscillatory manner, and therefore, the flow through the blood vessels is actually oscillatory in nature. There is a steady component also, but as I told you earlier, by linear superposition we can add up the flows due to the steady and the oscillatory parts. So, the differential equation that I had, okay, rho times duz by dt is equal to mu into 1 by r d by dr of r duz by dr, okay, minus dp by dz. Okay. This is now oscillatory in time. Okay. So, this is minus k cos omega t. Okay. Okay. So, this is a linear differential equation for uz, which is being driven by this inhomogeneous term. Okay, is being driven by this inhomogeneous term. And I have to find the solutions for this equation. Okay. This is oscillatory in time. Boundary conditions. Okay. uz is of course equal to 0 at r is equal to capital R. Okay. uz is equal to 0 at r is equal to capital R. At the wall of the pipe itself, the velocity has to decrease to 0. Okay. And then I have my symmetry boundary condition, duz by dr is equal to 0 at r is equal to 0. It is preferable to work in terms of scaled coordinates, okay, as always. Okay. The natural scaling for the radial direction is r star is equal to r by capital R. Okay. So, that gives me the spatial scaling. What about the scaling for time? Okay, what about the scaling for time? Okay. In this particular case, I am having the flow being driven by a well defined sinusoidal waveform with a well defined frequency. Okay. Since I have a well defined frequency, I could very well scale t star is equal to omega times t. Okay. The time period is 2 pi by omega, okay. The frequency is omega. So, I could define a scaled t star is equal to omega times t. Okay. What about the scaling for the velocity? Okay. The scaling for the velocity will come somehow from the pressure gradient that I am applying over here. Okay. Somehow from this pressure gradient, if that is large, the velocity will be large. If that is small, the velocity will be small. So, scaling for the velocity has to come out of the scaling for this pressure gradient. Okay. So, we will see how that comes about. If I just write down the scaling for the time and spatial coordinates, okay, I will get an equation of the form rho omega duz by dt star, okay, is equal to mu by r square. Okay, minus k cos t star. Okay, so, that is the equation that I get in terms of the scaled coordinates. Okay. Note that on the last term on the right hand side, cos of t star is dimensionless. Okay, cos of t star is dimensionless. Therefore, if I divide the equation throughout by k, okay, if I divide the equation throughout by k, then the last term on the right becomes dimensionless. Okay. By dimensional consistency, then every term has to be dimensionless. Okay. So, I divide throughout by k, okay, divide throughout by k, and I will get rho omega by k duz by d star is equal to mu by k r square. Minus cos of t star, okay, divided throughout by k. Okay. Now, the last term on the right hand side is dimensionless, that means that all terms are dimensionless just by dimensional consistency. Okay. So, I could define a scaled velocity by either dividing it by this term, okay, or dividing it by this term. Okay, I could use either one of those for defining a scaled velocity. Okay. If I divide a scaled velocity as mu u z by k r square, that means I am scaling the velocity by the viscous scales. Okay. Whereas, if I scale it by rho omega by k, then I scale it by the inertial scales. Okay. Typically, if the Reynolds number is small, you would expect viscous effects to be dominant. Therefore, you would scale it by the viscous scales. Whereas, if the Reynolds number is large, you would expect inertial effects to be dominant, in which case you have to scale it by the inertial scales. For the present, we will use the viscous scaling, okay, for the present case. So, let me define u z star is equal to mu u z by k r square. Okay. So, that is my definition for u z star. Okay. So, if I insert this into the equation, I am getting rho omega r square by mu d u z star by dt star is equal to 1 by r d by dr of r d u z star minus cos d star. Okay. And this is basically a Reynolds number based upon the frequency of oscillations in the tube radius. Okay. So, this I can define it as some number R e omega minus cos of t star. Okay. So, note that this is the inhomogeneous term, this is the forcing in time. Okay. This is the term that is forcing the velocity field. This is balanced by two terms. This one is a viscous term and this one is an inertial term. So, at high Reynolds number you would expect the inertial term on the left to be dominant. In the limit of low Reynolds number, the viscous term, the first term on the right, will be the dominant term. Okay. And then there are boundary conditions that at r star is equal to 0, du z star by dr star is equal to 0, and at r star is equal to 1. R is equal to capital R means that r star is equal to 1, u z star is equal to 0. Okay. So, I have to solve this subject to these boundary conditions. Note that the boundary conditions are both homogeneous. There is, however, a forcing within the equation, that is forcing the flow. Okay. So, let us see how we can solve it. This is a flow with an oscillatory pressure gradient. The equation, the conservation equation itself is linear in u z. Okay. The conservation equation itself is linear in u z. It is being forced by an inhomogeneous oscillatory term. Okay. So, a linear system being forced to a certain frequency. In this case, the scaled frequency is 1, okay, because when I scale the frequency, when I define omega t is equal to t star, the scaled frequency in this case is equal to 1. Okay. Therefore, the response also has to have the same frequency as the forcing. Okay. We did this earlier when we looked at the oscillatory flow past a flat plate, okay, when you had a bottom plate which was oscillating, okay, back and forth. It was oscillating with a certain frequency. Therefore, the velocity field everywhere in the flow also had to have that exact same frequency. Okay. So, rather than solve this equation, what we can do is to solve an equation. Okay. You know that cos t star, cos of t star is equal to the real part of e power I t star. Okay. Cos t star is the real part of e power I t star. Therefore, I can solve an equation for a complex velocity field, okay, defined by this equation R e omega du z plus by dt star is equal to 1 by r d by dr of r star du z plus by dr star e power I t star. Okay. Note that cos t star here, okay, this cos t star is the real part of this inhomogeneous driving term. This is the real part of this inhomogeneous driving term. Therefore, if I solve the equation for this complex velocity, okay, then the velocity u z that I get will just be equal to the real part of this complex velocity u z plus. Okay. Since the forcing term in my equation for u z star is the real part of the forcing term in my equation for u z plus, that means that the solution u z star will also be the real part of u z plus. Okay. This is always possible when we are working with complex variables. Okay. Okay. So, I will solve this equation for u z plus with boundary conditions partial u z plus by partial r is equal to 0 at r is equal to 0 and u z plus is equal to 0 at r star is equal to 1. So, I will solve this equation with these boundary conditions, which are the same as the boundary conditions that I had for u z star. Okay. These are the same homogeneous boundary conditions that I had for u z star. So, I will solve the equation for u z plus with these boundary conditions and then take the real part of that, and once I take the real part, I will get the solution for u z star in this equation. That is the strategy that we will follow for dealing with this oscillatory flow. Okay. So, how do we solve this equation for u z plus? It is being forced with a function of the form e power I t. Okay. In this particular case, the frequency is 1 in scale variables, omega is 1 in scale variables, is being forced with e power I t. Okay. That means that u z plus also has to have the form some function of r e power I t. Okay. It has to have the same frequency. There may be a phase shift, but the frequency has to be the same. A phase shift will basically be reflected in the complex nature of u z. Okay. The real, if there is no phase shift, it will be real. If there is a phase shift, it will be a complex number, and tan theta, tan of phi, where phi is the phase shift, will be equal to the ratio of the imaginary and real parts. Okay. So, I take this form of the equation and put it into the differential equation for u z plus, okay, and then solve it. Okay. So, this when I take this, so note that u z tilde that I have here is only a function of the radius. Okay, put r star there. It is only a function of the radius. Okay. So, when I take the derivative, okay, with respect to time, I will get r e omega times u z of r times I e power I t star. Okay, when I take the derivative with respect to t, I will just get I times e power I t star. Okay. And then I have a derivative with respect to r of u z plus. Okay. So, this will be of the form e power I t star into 1 by r d by dr of r du z plus by dr, sorry, okay, plus e power I t star. Note that within this equation all terms have e power I t star multiplying them. Okay. That means that I can cancel out e power I t star on each of these equations. I can divide throughout by e power I t star. Okay. And then I get an equation that is not dependent on time at all. Okay. It is completely independent of time, it depends only upon r. Okay. That is the reason that we were able to do this substitution in the first place. Okay. Because I knew that if I do the substitution, insert it into the equation, the time derivative will just give me I times e power I t. Okay. Once I have done that, there is e power I t on each of those terms, and I can just cancel those out, okay, to get r e omega into I into uz of r is equal to 1 by r d by dr of r duz by dr plus 1. Okay, so, this is the differential equation. I have reduced it from a partial differential equation in terms of r and t to just an ordinary differential equation in terms of r alone, because I know that the flow is oscillatory in time. Therefore, since the pressure forcing is of the form e power I t star, the velocity dependence on time also has to be of that same form. Okay, so, I have used that here. Okay. Good. So, now I can simplify this equation. Okay. I will get 1 by d square u z by dr star square plus 1 over r du z by dr, okay, minus I r e omega u z is equal to minus 1. Okay. So, I have taken minus this plus 1 to the left hand side, and I have taken the r e dependence on the right hand side. Okay. So, this is the differential equation that I have to solve in order to get what is u z. This is a this is a second order linear differential equation with an inhomogeneous term. Okay. First order linear differential equation. Let me just correct some things here. This is a first order linear differential equation with an inhomogeneous term. That means that I can write the solution as the sum of two parts. One is a general solution and the other is a particular integral. The general solution is the one that satisfies the homogeneous equation without the inhomogeneous term on the right hand side. Okay. The general solution is the solution that satisfies the homogeneous equation without the inhomogeneous term on the right hand side. Okay. That means that the general solution satisfies the differential equation partial square u z by partial r square plus 1 over r partial u z general by partial r minus I r e omega u u z general is equal to 0. So, this is the general solution, it satisfies the equation without the homogeneous term. Okay. And how do we solve this equation? We already saw what was the form of this solution. Okay. So, first thing first, I multiply throughout by r square. Okay. So, I will get r star square d square u z general by d r star square plus minus I r e omega r star square u z general is equal to 0. Okay. We have seen this equation before. Okay. We have seen an equation of the form x square d square y by dx square plus x dy by dx plus x square minus n square y is equal to 0. Okay. This is the Bessel equation, and the solution for these are the Bessel functions, okay, j n and y n. Okay. I can convert this equation to this form using the substitution x is equal to square root of minus I r e omega times r star. Okay. I can convert this equation to this form by using this substitution, x is equal to minus I r e omega times r star square root of. Okay. So, that this whole thing becomes just equal to x square. Okay. This whole thing becomes equal to x square. Okay. And as I said, these first two terms are equidimensional in R. So, they do not change if you scale R. Okay. So, the solution of this is of the form u z general is equal to C 1 j naught of square root of minus I r e omega r star plus C 2 y naught of square root of So, that is the most general form of the general solution. Okay. However, we saw in the 18th lecture that whenever you have an equation of this form, the Bessel function y naught goes to infinity minus infinity at 0. Okay. So, if the u z general has to be finite, that means that coefficient C 2 has to be equal to 0. If C 2 is not 0, then the solution will go to plus or minus infinity at r star is equal to 0. Okay. So, the central symmetry condition itself indicates that you cannot have y naught in the solution. The solution can only have j naught in it. Okay. So, this is the general solution. Okay. How about the particular integral? Okay. The particular integral is any one solution that satisfies the inhomogeneous equation, the complete inhomogeneous equation. Okay. Any one solution. Okay. So, it is easiest to choose the simplest possible solution that satisfies this inhomogeneous equation. The simplest possible solution in this case is just a constant. Okay. If I postulate that the particular solution is a constant, then these first two terms identically become equal to 0, because when you take the derivative of a constant you get 0 and you end up only with the third term. Okay. So, constant can satisfy this equation. Okay. So, the constant has to be of the form minus I r e omega u z particular is equal to minus 1. Okay. Or u z particular is equal to minus or plus 1 by I r e omega is equal to minus I by. So, this is the constant that will satisfy the differential equation. Okay. Yeah. Okay. So, therefore, u z is equal to minus I by r e omega plus C 1 j naught of square root of and C 1 is of course evaluated from the constant from the boundary condition that we have not yet used, right. So, there is the boundary condition. U z tilde is equal to 0 at r star is equal to 1. Okay. And using that condition, we can easily get the velocity profile as this gives us the final expression for the velocity profile, and you can easily verify that when r star is equal to 1, in this term the numerator and the denominator are equal, therefore, this becomes 1, velocity becomes 0. Okay. So, that is the final solution for the velocity profile. Okay. This is u z tilde. Okay. That means that u z plus is equal to minus I by r e omega to 1 minus okay, times e power I t star. Okay. And finally, u z star is equal to the real part. Okay. So, I have formally obtained a solution. Okay. I have obtained u z I'm sorry. I have obtained uz plus in terms of uz tilde. It has an e power I t star on the right hand side. Then I have to take the real part of this whole thing to get the actual velocity uz star, okay, as a function of time. Okay. What does this physically mean? Okay. I could of course take the solution for the velocity profile and then use that, okay, in order to calculate numerically how the velocity profile should look. Okay. But a better understanding is obtained by looking at limits where r e omega is small compared to 1 and r e omega is large compared to 1. When r e omega is small, that means that in this equation I can neglect the left hand side with respect to the right hand side. Okay. When r e omega is small, this left hand term can be neglected in comparison to the right hand term. Okay. And I will get 1 by r d by dr of r du z by dr minus cos t is equal to 0. Okay. And this you can easily solve. Okay. This can be solved quite easily. Okay. As if I neglect the take. Okay. So, this is the equation in the limit of low Reynolds number, okay. And I can solve this quite easily, okay, to get an equation of the form u z star is equal to 1 over 4 mu times 1 minus r star square times cos t star. Okay. And I can get the dimensional velocity by using the same scaling that I had. Okay. So, u z is equal to u z star into k r square by mu. Okay. This is equal to minus k by 4 mu into r square cos of omega t. Okay. This is a parabolic velocity profile. Okay. This is a parabolic velocity profile, the exact same profile that we would get for a steady flow, except that it has this k cos omega t dependence on it. Okay. So, this is a parabolic velocity profile for which the pressure gradient is the instantaneous pressure gradient at that particular instant in time. Okay. So, in the limit of low Reynolds number, we get something that is the same as a parabolic velocity profile, except that the mean velocity and the maximum velocity are oscillating in time with a frequency omega. Okay. This is in the limit of low Reynolds number. What does low Reynolds number mean? It means that the viscous stresses are dominant compared to the inertial stresses. Okay. One can have another interpretation of low Reynolds number. Okay. I can also define r e omega is equal to rho omega r square by mu, okay, which is equal to omega by mu by r square. Okay. Omega is the frequency 1 over the time period. Okay. Omega is the frequency 2 pi by t, where t is the time period. Nu by r square by nu is the time it takes for momentum diffusion across a distance r. Okay. So, if the Reynolds number is small, that means that the time it takes for the momentum diffusion across a distance r is small compared to the time period of oscillation. The time it takes for momentum diffusion across a distance r is small compared to the time period of oscillation. That means that the momentum diffuses throughout the tube instantaneously. Okay. It diffuses over a distance r instantaneously. Okay. And because of that instantaneous diffusion, the velocity profile is the same velocity profile that you would have at steady state, except that the pressure gradient in the velocity profile is the instantaneous value of the pressure gradient. Okay. So, the same velocity profile that you would have for instantaneous momentum diffusion, except that the pressure gradient is the instantaneous value of the pressure gradient. So, because of this, the pressure and the velocity are exactly in phase. Okay. The pressure gradient is exactly in phase with the velocity. Okay. So, this is the simplified solution for Reynolds number small compared to 1. The velocity is exactly in phase with the pressure gradient, and that is because the time it takes momentum to diffuse across the width of the tube is small compared to the time period of the oscillation. Okay, when the frequency is small, period of oscillation is large, the time it takes for momentum to diffuse across the tube is small compared to the time period of oscillation. Okay. So, that was when RE was small compared to 1. What about the case where RE omega is large compared to 1? Okay. I had an equation of the form I RE omega du z by dt is equal to 1 by r minus cos t star. When RE is large compared to 1, you would expect this term to be large compared to this one. In that case, can we just go ahead and neglect this term and solve the rest of the equation and get a velocity profile? Okay. Think about it. Okay, we will continue that discussion in the next class. It is a little bit complicated in this case. You should think a little bit more about this, frame this problem and see if you can get a solution. Okay. In the case where the Reynolds number is large. Okay. Is it possible to obtain a solution the same way that we did when the Reynolds number was small? Okay. This will give you some insight into the competition between diffusion and convection in these systems. This is the first such case where we actually analyze the balance between convection and diffusion. In this particular case, it is not exactly convection, it is an unsteady term, but proportional to the Reynolds number nevertheless. Okay. So, we will continue this class, the oscillatory flow in the pipe in the limit of high Reynolds number in the next lecture, with a particular emphasis on the ratio between inertial and viscous terms. We saw that when the Reynolds number based upon the frequency and the pipe radius was small, you could neglect the inertial terms and get a solution which looked like a steady flow. When the Reynolds number is large, what happens? We will briefly discuss this in the next lecture before we go into the next topic. The next topic will be on transport in another curvilinear coordinate system. In that case, it is called a spherical coordinate system appropriate for objects with spherical symmetry, like spherical particles and so on. So, we will continue this, finish it in the next lecture and then go on to transport in spherical coordinates. So, with this we will end this lecture. We will continue this in the next class and we will see you next time.